All right, so today we are going to talk about the halting problem. This is a big deal. The halting problem. The halting problem is a sort of decision problem. If I give you a Turing machine and a string, can you tell whether or not that Turing machine will halt with that particular input? So I will say it like this. Given some Turing machine M and a string X, can you determine if M halts on X? And by halts, I mean either accepts and stops, the machine stops after it accepts the string, or rejects and stops, but no infinite loop, right? That's what is meant by halt. Can you determine if the machine will halt with that particular input? This general question is called the halting problem. And the halting problem, like I said last time, the halting problem is the most famous example of a problem which cannot be solved by a Turing machine. And I want to tell you why no Turing machine can answer this question in general. Given some other Turing machine and a string, can you tell if it's going to halt or not using that string as the input? All right. We can actually consider sort of a language version of this, and I'm going to call this LH. This is the whole problem kind of turned into a language of strings, and those strings will look like M with a separator followed by X, where M is a Turing machine and X is some input string, and M halts on X. That is to say, when you run M as a machine using input X, it actually stops. It doesn't loop forever. It either accepts or rejects while stopping. All right? When I say M is a Turing machine, what I mean by that is it is some kind of an encoding of a Turing machine into a string, because this is a language of strings. M has to be encoded as a string. So, and there are many ways to do this. Translate a Turing machine diagram into a string. It is possible to do that. It's not terribly difficult. But I hope you're all familiar with the fact that like any kind of information can be translated into a string by just sort of digitizing. So you choose some kind of method to encode the Turing machine as a string and make a language out of it. Yes?
How can we make sure that it doesn't infinitely loop?
How can we make sure? I'm not sure what you mean. I'm defining a language which consists of all strings that look like some machine followed by X, where that machine does not loop forever. The question of how could you actually figure that out for a given example is not obvious at all, but you can still define this as a set. It is the set of all machines and their inputs where it actually does halt. All right? And this is called LH. I'm going to refer to this as the language of the halting problem. That's what the little h is for. All right. M is a Turing machine. That's it. It's a Turing machine. It is not necessarily a total Turing machine, which was one bit of terminology we had. Total means that it never loops. It never has infinite loops. So this is not very interesting if M was always a total machine, because the question is about whether things halt or not. Total Turing machine always halts. But in order for this set to be interesting, you need to consider some non-total Turing machines. All right, so this language, LH, is what we're going to be talking about for the rest of today. I hope it makes sense. It's a very weird language, but it consists of string representations of a Turing machine together with some input where that machine actually halts on that input. Very strange, but we are going to ask, is this recursively enumerable, or is this recursive? That is to say, remember, recursively enumerable means, is it the language of a total Turing machine? And this means, is it the language of any Turing machine? All right. This is very strange. LH is itself a language that's made up of Turing machines, right? And their inputs. And now we want to talk about, is that language something which can be computed on some other Turing machine? It's just very weird, and actually it's only going to get weirder as we go along today. It turns out, so what we're going to show is, well, actually it is I'm sorry, I have these backwards. RE means, sorry, I wrote this backwards. The word total is in the wrong one. RE means the language of any Turing machine. Recursive means the language of a total Turing machine. Sorry about that. Remember, total means the machine is not allowed to have an infinite loop on any input. So yeah. Total means the machine cannot ever have infinite loops. All right. The first question, is it RE? Actually, that is not so hard to answer, and the answer is yes. So LH is RE. In order to explain why, I have to describe to a machine for which the language LH is accepted on this machine. But that machine is allowed to sometimes have infinite loops. And actually, the machine which accepts LH is the universal machine. So let U be a universal machine. That is, it can simulate another Turing machine. And so when the input of U is M hashtag X, what U does, the whole point of the universal machine, is it runs a simulation of the machine M using the input X. All right, so when the input of U is M hashtag X, people don't really say, I think people usually say hash. Hashtag is like a Twitter thing that now everybody says hashtag, but it's not what people didn't say that before a few years ago. When the input is M hash X, what happens? Well, the way the universal machine works is it just runs a simulation of M. And so what that means is if X is accepted on M, then U halts. Because U is running a simulation of M acting on X. And if X is rejected on M, then U also halts. And if X loops forever, then U will also loop forever, because the whole point of U is it's running a simulation of the machine M. So if X loops forever on M, then U loops forever. But in any case, we can make it so that either of those haltings are accepting. So we can make it so that U accepts whenever M halts on X. You just arrange it so that any accepting or rejecting halting of this M results in U accepting. The only thing you can't do is handle these forever loops, because when M loops forever, the simulation U will also loop forever, and so you're just kind of stuck. But when M actually does halt, either accepting or rejecting, you can make it so that U accepts in either of those cases. In any case, then the language accepted by U will be this language. It is the language of Turing machines followed by strings which halt. All right? So that means LH is RE. That is, it is the language of some Turing machine. That Turing machine, though, is not total. U is not a total Turing machine because sometimes it loops forever, because it's running simulations of other Turing machines and they can loop forever, and so U also sometimes can loop forever. All right, so LH is RE, but, and this is what's slightly crazier, we're going to talk about LH is not recursive. So in that sort of hierarchy of languages, we had the regulars, the context frees, the non-context frees, but recursive. So this is context-free languages. These are recursive. For instance, A to then, B to then, C to then is not context-free, but you can do it on a Turing machine. The next level out would be RE, that is, and it turns out the language out here is this language, the language of the halting problem. I don't know if you were hoping for, like I kept on telling you, there is going to be some language out here, and it's going to be totally crazy. You cannot write any example with like A to the N, B to the N, that kind of thing is not going to cut it. The languages in this region here have to be totally crazy. And this is the simplest example that there is of one of these languages. Yeah.
I was just gonna, so like RE languages aren't recursive, they're just like their own thing.
Yeah, this would mean a language which you can get to run on a Turing machine, but that Turing machine sometimes will have infinite loops. That's what this means.
Okay.
Yeah. As opposed to these things you can do on a Turing machine which never has an infinite loop, which is essentially all the examples we've ever done have been in this category. All right. So I need to explain this. Why this? That's really the big deal about this language, the language of the halting problem, why people care about it. So I'm going to write this as a theorem. It's LH is not recursive. All right. And I want to go through the argument here because there's something very interesting. Like the argument that's used is very, very weird, and I think really interesting to look at. So let's do a little proof here. This is not going to involve super technicalities in the proof, but it will involve a very weird kind of logical conundrum, which I think is interesting enough to mention. Anyway, what we're going to do is you basically have to do some kind of a proof by contradiction. So I will say, to get a contradiction, we're going to assume that it is recursive. Assume LH is recursive. I.e., what that means is that LH, that there is a Turing machine, which I will call, which doesn't actually exist, but I'm going to say, assume we have a total, meaning it never loops, it only accepts or rejects, whose language is LH. All right? Assume that we have a total Turing machine whose language is LH. What we can do in that case, we'll look at what happens. This is the crazy idea. For strings like M#M, What if you try to run the Turing machine in a simulation using itself as the input? This is what this is the crazy idea that's at the basis of this proof. We're going to look at what happens when you try to run this simulation of a machine using itself as the input. Weird things happen. Check it out. We're going to look at what happens for strings like this. So using our total Turing machine, that is, we have a machine that can always tell you if M is going to halt on X or not. All right. So what we can do is we can build another machine, which I'm going to call H, such that this is actually not possible to do. We're arguing to get a contradiction. So this machine H is actually not possible. But I want to build a machine H such that, first of all, H accepts any string that looks like M, hashtag M, whenever M does not halt. With input M. So if you run M on itself, let's say that this other machine is going to accept when that run M on itself loops forever. Ordinarily, a Turing machine is not able to decide, but we are assuming for the sake of a contradiction that we do have a Turing machine which can decide if it's going to halt or not. In that case, you can make this work out. And second of all, H rejects, I'm going to say H loops forever on M hash M whenever M does halt on input M. So we're kind of making it do the opposite. If M does not halt, you make H accept, and if M does halt, you make H loop forever. Yes?
Wouldn't M simulating M just be like the same thing? It would be the same machine because it's like it's simulating itself kind of?
It's not really simulating itself, it's using itself as its own input, which usually wouldn't really mean anything. That you should feel like is not really meaning much of anything. I'm trying to think of a cute example comparison that I can make, but yeah, it's not that M is simulating itself. There's another machine. This H is taking strings like this and somehow figuring out if they halt or not, and then H will accept when M does not halt, and it loops forever when M does halt with its own input. I suppose it's maybe like you could write, say, a Python code that say takes a giant string and turns everything to uppercase, and then you could say, whoa, what would happen if I ran my own Python code through that? And the answer is, well, it would just make it all uppercase. I mean, that's not really, it's not terribly interesting then. But this is doing that same sort of thing. What would happen if you ran the machine with its own self as its input? The answer is, I don't know, it would do something weird, I guess, but nothing necessarily special about it. It's just a weird thing that you could do. What's special is how this results in a weird contradiction in the proof here. So the big question now is, if I make a machine H which has this kind of behavior, what happens when we do, I will say when we run H with input H hash H Now we're getting, like, this is sort of bringing this kind of self-reference to another level, all right? We are running this machine H, which is all about running Turing machines on themselves. We are running this Turing machine on itself in a weird way, all right? And what happens, the question is, does this halt or not? That's the question. There are two options. Either it halts or not, right? We will see both will lead to a contradiction. Either is contradictory. This is kind of like, you will see in a moment, it's kind of like the old situation where someone who says, like, I always lie, and it's like any way you interpret that conversation, that statement is immediately self-contradictory. It's the same situation here. There are two options. What happens when you run H with input H hash H? Either it halts or it doesn't. So I'm going to just consider these two cases. If it halts, look at what happens. That means that if H halts with input H hash H, then by number 2 here, it says H loops forever on this input whenever M halts. So if H halts, I'm getting myself confused here. Whenever M halts, if it halts, then by number 2, then H will loop forever. Because the whole point of H, it is constructed so that it loops forever whenever its input actually halts. All right? But that is immediately contradictory. I said if it halts, then that means it will loop forever. And then the other way around is also true. So if H loops forever, with input H hash H, then that means whenever M does not halt, that means it should be accepting, which is, again, a contradiction. So this, by number 2, then H will accept. But both are immediately self-contradicting, like with their same cases. So these are both self-contradicting. And that's where the proof ends. The entire thing is a contradiction, because either of these cases produces these kinds of logical paradoxes. Yes?
So for the halting condition for H, why is that number 2 and not number 1?
Number 2 is about what happens when the machine halts on its own input.
So, like, when M halts, that means that H halts.
Yeah, this M is not a particular machine. You can run H on any input that you want for any machines. The question is, what happens if you run H on itself, H hash H? And the answer is, if H halts on H, then that computation will loop forever, which is the opposite of halting. And the other way around too. If H loops forever on H, then that halts, which is, again, the opposite of what it's supposed to do.
I guess it's like, why is it that rule versus like 1? Something. I know that that's like the whole contradiction, but like, I don't know, like, how do you know that 2 means that it like halts but doesn't halt? I guess, like, versus
Number 2 says whenever M halts on input M, H loops forever. And then we are considering this where M equals H. So whenever H halts on input H, then H loops forever.
Okay.
And so if it does halt, then because of number 2, H will loop forever.
Okay.
Yeah. If this seems very weird to you, then I agree. It is very weird. All right. Anyway, this is the contradiction. We are boiled down to 2 options, but both of them are immediately paradoxical, like self-contradictory. So that means the whole thing, so this H cannot exist, which is the whole point of the proof. So that means LH is not recursive, right? It is out here in the RE domain, but it's not recursive. It is not recursive. All right. Very strange. This is one of the sort of landmark proofs of the 20th century, in my opinion. It is very weird, and to be honest, every time I look at it, I end up getting myself confused again. I feel like I'm not, I am a mathematician. My area of research is not in the theory of computation, so I'm not exactly an expert on this area. I get the feeling that some people can just sort of walk around living their lives feeling like they totally understand this proof, and I am not really one of those people. I feel like I understand it sort of temporarily, and then I lose track of it. If you ask me about this next week, I will have to go look back at my notes very carefully to reconstruct this argument. All right, there are practical applications to this result, and there are things probably that you know on some intuitive level from your experience programming. So one application of this, perhaps not a useful application of this, but what this means really is in a real life programming language or on a real life computer, there can be no general purpose infinite loop detector for real programming languages. I don't know if you ever wished for this, or if you've ever thought about this, but wouldn't it be great, for instance, the Python interpreter, when you write your code in Python or whatever, you run it through the interpreter or the compiler, and if you have errors, it will tell you about the errors. At least it will tell you about some kinds of errors. I don't know if you ever thought about it. Wouldn't it be great if the compiler could detect if I'm going to write a loop which will run forever? I don't know if that's ever happened to you and you thought, like, man, why didn't they tell me that was going to happen? Yeah, how would you figure that out? I mean, as a programmer, that's not my job to figure that out. That's the compiler's job. I mean, don't you feel like, wouldn't it be great if the interpreter could figure that out? Why don't they do that? Or if not, is there some guy somewhere working on that, trying to figure out how to make that work? The answer is no. That is all impossible. It's not possible to have a general purpose infinite loop detector, because if there were such a thing, then that would mean you have solved the halting problem, which, if you believe what I just said, is actually impossible. And actually, if you think more deeply about this, it would be totally crazy if there was an infinite loop detector. I don't know if you've ever really thought about this, but here's a little thought experiment. Think about it. If there were an infinite loop detector, general purpose, an infinite loop detector, you could use it to do totally crazy things, at least in my opinion, crazy things. If there were an infinite loop detector, for example, I don't know if you're very knowledgeable about the state of unsolved problems in number theory. Mathematics has a lot of unsolved problems. There are many unsolved problems that people are working very hard on. One of them, I will just choose at random, the problem of perfect numbers. Anybody heard of perfect numbers? A perfect number is one which is the sum of all of its divisors, other than, including one. Like 6 is a perfect number. 6 is 2 plus, 3 plus 2 plus 1, right? It is the sum of all the divisors other than itself. That's a perfect number. The next perfect number is, I don't know, 28? You know this? All right, great. Oh, you looked it up. Okay. There is a major unsolved problem. So this is called a perfect number. One of the biggest unsolved problems in number theory today is, are there an infinite number of perfect numbers or not? Or are there only finitely many? Actually, there are only finitely many known perfect numbers. but it has not been proven if there are actually infinitely many. I think most people, I'm not a number theorist, but most people in this business believe there are infinitely many, but it's not been proven. Yes?
I don't know,
You have an opinion?
I don't know, I'd like to think that if there's like, if you could say there's infinite numbers, then there have to be infinite numbers. Because like, if numbers go on forever, eventually
I mean, yeah, numbers go on forever, but it's like, is there, are there any even numbers that are not divisible by 2? No. But you say, well, the numbers go on forever. Maybe someday we'll find one. No, you're not going to find one. Nobody knows, though, right? So anyway, here's my brilliant way of solving this problem. All right, without any knowledge of number theory, the greatest number theorists in the world have been trying to answer this question: are there infinitely many perfect numbers? This is unknown. Check it out. Here's a little Python code here. I don't know if this is legal Python, but I'm going to say, I'll just say do. Can you say do in Python? It's going to loop this block forever. And it's going to say something like, well, I'll start n equals 1 here, or maybe 2. 1 is a weird special case, but I will say if n is perfect. And it's easy to check if a given number is perfect or not. You just write down the divisors and add them up and see what you get, right? So if n is perfect, break, I believe, is that legal in Python? Some languages have a break. This will just break out of the loop and stop. Do is illegal?
There's no do in Python.
Can I say while?
Yeah.
While true?
Oh, true, yeah.
That's what I want. Whatever. It's not necessarily an infinite loop because of that break inside, right? And then I say n equals n plus 1, and then this is my whole loop, all right? Now, this is the stupidest way ever to try to tell if there are infinitely many perfect numbers. All it does is it just checks every number forever, which is not going to work because of that, the F word, forever, right? But if there were an infinite loop detector, you could use it on this code, and immediately you will have solved the problem. If there are infinitely many perfect numbers or not, right? That infinite loop detector, I don't know if you can imagine how simple would it be? It would have to be very, very hard. Like, it would have to be sophisticated enough to, on its own, prove the perfect number conjecture one way or the other, right? And pretty much any other question you can imagine in number theory could be phrased in this way. So if you had an infinite loop detector, it would basically end mathematics as we know it, because you could translate any mathematical theorem into some kind of stupid brute force loop like this, and then run your infinite loop detector on that loop, and it would tell you if it's ever gonna terminate, if it's ever gonna halt. So I hope that I'm convincing you. If you didn't like the proof, you should at least now believe that the halting problem, probably it wouldn't make sense if that was really possible to do. An infinite loop detector would be so sophisticated that it would basically be able to prove any math theorem, which should seem suspicious to you. At least any math theorem that can be boiled down to some kind of countable enumeration, which is really not every theorem. But.
So it basically, like, it would tell you whether a loop would stop or not eventually?
Yeah, that's the idea. And if you had some way of telling if this loop ever stopped, then that would be equivalent to knowing if there were finitely many or infinitely many perfect numbers. All right? So, an infinite loop detector is definitely impossible. This is because the halting problem is not solvable. And if the halting problem were solvable, you'd be able to basically answer any mathematical question without any real insight into anything. All right? This will immediately tell us about how to make a Turing machine with actually more capabilities than the Turing machine, the ordinary Turing machine. Like I said last time, any improvement that you can think of does not actually give it more capabilities. But now actually we see something which a Turing machine is not capable of. It is not capable of deciding a halting problem, all right? And so you can a Turing machine can actually be improved by giving it more functionality. And this is what I said last time about, I said anything you can think of is not actually going to make the machine more powerful. But there are things, just you would never think of them on your own. This is what I was talking about. A Turing machine can actually be improved by making it able to solve the halting problem by some magic. Making it able to solve a halting problem. Because an ordinary Turing machine is incapable of solving a halting problem. So if you want to make it do things that it couldn't do before, you just let it solve a halting problem. All right? This, I suppose this Turing machine would immediately be able to prove any theorem that it wants to from number theory, which is, makes it, I mean, it would be kind of magical. Like such a machine cannot really exist in the actual world. But in a theoretical level, you can say, these things, this is called a Turing machine with halting oracle. It has I'm not making that up, it has a cute and sort of magical sounding name to emphasize the fact that there really is no such thing in the actual world as a machine which can solve a halting problem. But if you imagine a machine which had some kind of extra magical ability, then it would be more sophisticated than a Turing machine. So it is possible to make Turing machines more powerful abstractly. It's just not actually possible in the real world. We have 15 minutes left today. I think it's interesting to think about, and maybe I'm going to get a little philosophical here. And this is something I would encourage you all to think about. Talk to your friends and loved ones about this. We could put all the desks in a circle if they were more movable. I never put the desks in a circle. But in the real world, a Turing machine, when I say Turing machine, in the real world, you should think of like actual computers, right? So real computers have the same limitations as Turing machines. I hope you believe me. That's because a real computer on some level is like a Turing machine with a tape. It has a memory and it can access that memory at certain locations as it does what it does. Because it's a machine which is based on a memory and looking sequentially at locations of memory, it has the same limitations as Turing machines. What I would encourage you to think about, this will not be on the final exam, what about people? Human beings, human brains. Are they like Turing machines or are they something else? Now, I suppose this is a matter of opinion. This is not exactly a mathematical question anymore because a person is not a mathematical concept with a definition, a mathematical definition. But I think it's an interesting question to think about. A human brain as a instrument of computation is not fully understood how the human brain works. But I think that most people would agree that the human brain is a physical object which obeys the laws of physics. It's not doing magic in there. At least that's, I don't know. Does everyone believe that? I'm not sure if everyone believes that. But can I say, I'm going to try to write things which are uncontroversial. The brain is a physical object, right? Which apparently has something like memory. I mean, in some way which is analogous to, say, computer memory. And I will say probably, I don't know, this is maybe my own opinion, behaves according to the laws of physics, right? I think that means it's basically like a Turing machine. I mean, I don't know. You'll have to think for yourself about what exactly that means. But this suggests to me that I would say probably the brain is basically a Turing machine, right? When I say is, I mean probably certainly you can simulate a Turing machine using a human brain, because like I can think about a Turing machine and decide what would happen. But probably the other way is also possible. You could simulate a human brain using a Turing machine. And I think people generally believe that if you could, for instance, scan my entire brain at this moment with perfect detail and load it into a computer, you should be able to emulate or run a simulation of my brain in a computer. I think most people believe that is in principle possible. This should make you think things. I don't know about. I think so. Here's my own perspective. This is what I personally think about this, and I'm not gonna try to instruct you how to think about this. But I was raised as a person of faith, and I remain a person of faith. I believe that there is such a thing as a human soul or something. I believe that human beings are of value in a way that, other things are not. I don't know if you agree, and you don't have to agree with me, but this makes me think hard thoughts about, like, if the human brain is the seat of some kind of divine nature, or at least some sort of eternal nature, then can another Turing machine? I feel like that somehow means that other Turing machines could also be like an eternal soul or something. I don't know how anybody feels about this, but to me, if I want to feel a certain way about the human brain, and the human brain has some kind of special significance in my view of the world, I must ascribe that same significance to other Turing machines. Because, I mean, this is, I don't know if you agree, but this is the thing that I think about. You have another thought?
I mean, for example, let's say the brain is like a Turing machine, but it's infinitely more complex.
Yeah, like for instance,
Like
this.
we talked about complexity.
Yeah, this here is also a Turing machine. I do not believe that my phone has some kind of eternally valuable soul to it.
The fantasy is infinitely more complex than would the fantasy that affects your.
Yeah, so he says my brain is infinitely more complex than this. I would say it is more complex. I don't know about infinitely more.
Currently.
Yeah, like to me, I feel like my phone right now does not have a soul, but I cannot rule out the possibility that some kind of super complex version of this could at some point be just like me, right?
Yeah.
Our view of what I'm trying to say is that our view of thing can be affected by the quantity. For example, one thing doesn't mean much, but a trillion dollars means a lot. So if it's complex enough, then maybe the big mind can change.
Yeah.
Or artificial intelligence.
Right. I mean, this has to do with artificial intelligence and if you believe that artificial intelligence is possible, then to me there's a deep kind of spiritual dimension to that also. If you even believe that there is any such thing as spirituality, then in my opinion, that must mean something about how you approach computing machines. And I'm comfortable at this point in my life with being sort of disrespectful of my computer. But maybe 100 years from now that I'll have to think about that morally. Yeah, what do you think?
Yeah, well, I think that, like, if you think about it, like, when we're talking about computers or Turing machines, because they have, like, an internal tape and, like, memory bank and everything,
Mm-hmm.
I feel like, at least in my opinion, like, to say that the brain is fully a Turing machine, we have to understand how we store memories and where those come from, because we still,
Right.
because I feel like memory is one of the most abstract things that we talk about.
Yeah, right. Yeah, and I don't claim to know how the brain works, but I assume that it does work according to some mechanism that people will figure out eventually. And I can't imagine.
Will that?
Hmm?
Will they? That you assume they want to figure it out. I mean, we are constrained by our own.
Yeah, I mean, maybe it's too complex for us to ever figure out. I don't know.
I mean, because we are basically operating a bunch of things.
Yeah, I don't know. Maybe I'm overly optimistic, but I feel like even if human beings never really figure out how the brain works, it still seems to me possible to just brute force simulate a brain in a computer.
Yeah, I think that's possible.
I don't know. Maybe that's not possible. But
Theoretically possible.
yeah.
Because even if you count physical resources, it's limited.
Yeah, I mean, I suppose there's an engineering issue, and there's like a theoretical mathematical issue. Is it even possible? I feel like it probably is possible, mathematically speaking. As an engineering endeavor, maybe not. But even so, this causes me to have sort of moral questions. So like I said, I hesitate to share my own opinions just because I'm not trying to make you feel any particular way, other than recognizing that this is an interesting question. I think somebody who is, say, total like naturalistic, atheistic, anti-spiritual at all, which I don't mean to disrespect this. Maybe this is less of an issue to such a person. I'm not sure. But I think even such a person recognizes on some level that their own self, their own mind is kind of special to them. I don't know.
Comments on this YouTube video.
Yeah, maybe these YouTube commenters. Yeah. Yeah, they can fight amongst themselves. I'm not trying to fight. I just want to. My goal in bringing this up at all is just that you would all. I hope that what we can all agree on is like these are interesting questions that deserve to be thought about by each person. You don't have to think of it so that I can evaluate what conclusions you make, and you don't have to make conclusions. Yeah.
I just want to point out that brings a really strange paradox to how I thought about it, of how like if I was just saying that the brain can't be a Turing machine, yet eventually I think AI could be a thing that's kind of contradictory because AI in itself would simulate how we think.
Yeah.
That's weird.
I feel like I worry. Say some more things that will make them really hate me on YouTube. But, yeah, I don't mind them hating me on YouTube. So my own background, I'm a Christian, but I am continually like super disappointed with the way that like loud American Christians conduct themselves in public discourse. But I think like what I don't want to see happen in the future is like real AI comes along and somehow human beings feel like, well, we have real intelligence and they are just created intelligence. Like, I don't think there should be such a distinction. This is a very hard thing for Christians in particular to think about though, because I'm not like a biblical literalist about these sorts of things, but if you believe that human beings were sort of created by God to play a particular role in the history of the universe, then maybe there would be a difference. I don't know. It's a hard thing. When Jesus died on the cross for people, did Jesus die for the robots too? Like, do they need to pray or whatever? Like, these are strange questions that I don't have answers to these questions. If the robots are watching this YouTube video in the future, maybe, yeah, I don't know how I feel about the robots. All right, I think it's about time to go. We'll talk some more mathematics next time. I hope this is interesting to think about, though.